Sounds good. I guess I'll intro us off. Um, yeah, hi everybody. Hope you're all doing well today. Welcome to our Intro to AI workshop. We're so excited to kind of, get you started on this technical workshop and hopefully give you insight into something that, surely all of you might be interested in, no matter your skill level, but also might be able to use on your project depending on what you're building. So with that being said, I guess I'll just hand it off to Jeffrey, who can take it from here.
All right, hey everyone. I'm Jeffrey Lai. I'm a junior. I'm studying physics, and I'm going to be giving this workshop today. So if everyone could, please go to this link right here. That would just be github.com/jbial/hackillinois-ml-workshop. Okay, and then once you're here, you're going to want to clone this repo. So you can just click on code right here, click on the clipboard, go to a terminal, type git clone, paste the link. Okay. So now you should have that in whatever directory you were just in. And then go ahead, cd into that, and then I'll wait here if anyone is having trouble. How are we taking questions, by the way? Through the chat?
Yes, on the chat, I actually just posted a link to Slido from where attendees can kind of just answer questions. And then I can get to see those and I can ask you those from there.
Okay. Okay, so I'll just move on for now.
Perfect.
Okay, cool. So then once you're in here, following the README on the GitHub page, you're going to want to run this command, pip3 install-r requirements.txt. And basically what this is going to do is just going to install all the necessary packages you need for this notebook to run. So I already have a lot of them, so it's going to say requirement already satisfied for a lot. Okay, and now we want to run the second command, which is cp, and then we're just going to make a copy of the main notebook. This is because we want to keep that main notebook as a reference in case we get stuck or something breaks, and then we can go back and check. So you can call it whatever you want. I'm just going to call it copy, and it should be there. Okay.
Jeffrey, could you share your screen by any chance, if possible?
Oh, yeah. I'm sorry.
Yep. Okay, you're co-host now. Go ahead and share your screen.
Sweet. All right. Okay. Yeah, I'll wait here, I guess. Do you see anything in the Slido? Any troubles?
Yeah, so we were just getting questions about GitHub on Slido. Yeah, those are now hopefully resolved. I just confirmed that the GitHub link is working for people. So yeah, we should be fine.
Okay, cool. Yeah, so just make sure you go to this link, clone the repo, and then run these two commands in the terminal. The first one is essential. The second one, not so much, but it would be helpful. Okay, I'll move on. So from here, we're going to have our copy. And so we're just going to run Jupyter-notebook. It should have been installed with that pip install requirements command. So we'll just run Jupyter Notebook and we'll open one up on this directory. Okay. So let's go ahead and open up our copy. And then we'll have our notebook open, and then I guess I'll have another checkpoint here just in case anyone is having any trouble. Okay, cool. So I'm going to assume that we're all up to speed at this point. So I'm going to go ahead and get started on the tutorial. Okay, so welcome to the Hack Illinois 2020 Intro to ML in Python technical workshop. So basically today we're going to be taking a very deep dive into a very basic machine learning concept, and that would be regression. And so I'm sure many of you have heard of regression, but I'm not sure many of you have gone this in depth into regression before, in an actual data set. So the table of contents are going to include, first of all, an overall overview of machine learning. I'm going to assume that you guys have no experience in machine learning, so I'll just have a quick overview. Then we're going to talk about how to deal with data, and then we're going to talk about the actual linear regression model and how to optimize and how to get the solution. And then we're going to talk about regularization. Okay, so for notation, really quickly, because there's a lot of math in machine learning, so you have to be comfortable reading math, and the notation is very important. It's not always the same. So lowercase, unbolded, unitalicized letters are going to be scalar variables. Bolded lowercase are going to be vectors, and then bolded uppercase are going to be matrices. Okay, so machine learning. On a high level, the goal of machine learning is to leverage models or algorithms that can learn from data so that we can reason about the actual data generating processes of the world. So this is all around you, actually. This occurs in science. So like the way Newton first discovered the laws of gravity is he had to observe the planetary motion, and then from that data, he had to extrapolate the model, which we now know as GMM over R squared, or whatever it is we learned in physics. And so this is a very fundamental thing, right? We observe data and we want to build models on that data. And so this naturally has applications in many fields. So these fields include business, medicine, engineering, and engineering is already a huge field on its own. Physics, transportation, real estate, finance, military and defense, commerce. And that's just scratching the surface. So here's a bunch of cool GIFs of really cool machine learning applications. So object tracking, this is basically you want to track objects in real-time video. Pretty self-explanatory. It's really cool. And you can see this has obvious applications if you're a company selling cameras to stadiums and you want the cameras to track the balls so that these action replays look nice on TV. Second one is robotics and control. So here we see this linkage robot basically just doing basic actions in the kitchen. Pretty cool. So imagine just having like an automated kitchen robot, I guess. Third one is image semantic segmentation. So on the left here is a raw video feed. On the right is a video feed where every pixel is assigned to a certain class. So you can see the blue pixels correspond to vehicles. The dark purple corresponds to the street. Light pink, purplish corresponds to the sidewalk. Pedestrians correspond to red. And then foliage, I guess, trees and stuff corresponds like yellow. And so this has obvious applications to things like self-driving cars, where you have to basically understand your surroundings in order to make decisions and not hurt anyone. The next one is something that we've probably all touched before, and this is machine translation. And so recently, I guess like 3 years ago, there's been an explosion in machine translation technology based on neural networks, and it works really well. And so if you've ever used Google Translate, you've touched a neural network, and this is one of the bigger success stories of machine learning. And the list goes on and on. The next one, protein folding. Why do we care about protein folding? Well, because proteins, if we understand proteins, then we can design drugs that interact with certain proteins in certain ways. So we essentially have control over how effective drugs are on humans. And so this has obvious huge medical benefits. And so we see here that so the ground truth is the green, And then the model prediction is the blue, and we see that the blue is pretty close to the green. And so this was a recent advancement done by Google DeepMind on protein folding. This was a pretty big breakthrough. Last one I'm going to talk about is weather prediction. Like I said, machine learning has its natural place in physics because we observe data and then we want to make models on that data. And so here on the bottom is the ground truth of, like, I guess, a storm cell moving across the northern United States. And then on top is Google's MetNet, which is basically, it just predicts the weather. And we see that over time, it matches the ground truth pretty well. And so the list can go on and on and on. Those are just a sample. So it has applications in many, many different areas. Okay. So generally, machine learning algorithms fall into 3 categories. You have supervised learning, which involves learning from labeled data pairs. Often in practice, getting labeled data is very expensive because you need something to label the data. And this would be human labelers or sometimes even automatic labeling with machines. But this is kind of more sophisticated. Actually, some cases where you're providing labeled data and you may not even realize it is if you use hashtags on Instagram. The hashtags act as labels for your Instagram post. Instagram uses those images as training data. For Google, the CAPTCHA images, where it's like pick the tiles that have a car, that's another way that they get data for images. For text, for Google's "Did you mean this?" that's also a way to get kind of a label for text data. And so, yeah, so people are getting more and more clever with how you gather labeled data, but still it's harder to get than unlabeled data. And unlabeled data is what unsupervised learning is concerned with, learning from unlabeled data. And there is plenty of this, right? Just think of the internet. So you can get however much data you want from the internet, doesn't have a label. And then finally, semi-supervised learning is a mix of unsupervised and supervised learning, where you learn from a mix of labeled and unlabeled data. Often the labeled data set is much smaller than the unlabeled data set. Okay, and like I said before, we're barely scratching the surface. Okay, so let's go ahead and just import our packages that we need. So go ahead and run Shift Enter on that cell, and then I'll wait here for any bugs or whatever. Anything in the Slido, Raghav?
Nope, not as of yet, but this is a good reminder that if people do have any questions, definitely put them in Slido. And we'll be having like checkpoints throughout the presentation, actually, where we'll be able to get to those questions and answer those. So yeah, definitely don't hesitate to put those in there.
Yeah, please don't hesitate to bring up any issues. Okay, I'll move on. So the next section is data. This is the most important part in machine learning. It's not the models, it's not the neural networks. This is the most important part. So working with data when you're working on a machine learning project is going to take a significant amount of time if you're doing machine learning in practice. Now, I'm not talking about like importing the MNIST data set and then fitting like a neural network to it. Okay. I'm talking more about getting actual data that's noisy and not cleaned and all like the MNIST data set is. So academics like to call this in the wild. This is the common terminology for that. Just means like in real life. So there's many possible nuisances that you can encounter when you're working with the real world data set, such as noise corrupted data. If your model is fit onto a Tesla, right, and then your Tesla has sensors that takes in data from the world, those sensors are not going to be perfect. So there's going to always be noise if you're using sensor data. Missing values, this is also very, very common. So sometimes for a tabular setting where you have tabular data, you'll have some cells that are just missing, and you have to fill them in with something, right? You can either throw away that data, which is undesirable, or you can fill it in with something intelligently. Incorrect labelings, like I said, labeling has to happen by a human or something. So humans aren't perfect, they make mistakes. So there is cases where labels can be incorrect. Duplicate examples, that can cause problems in the actual training of your algorithms. Mixed data types, this is not really a nuisance, but it's something that you will encounter. In fact, we're going to encounter this today, where you'll have columns of, say, real numbers, but then you'll have other columns of like text categories. So a mix of numerical and categorical data. Large magnitude differences. So imagine if you have one column that on average has a magnitude of 1,000,000 and another column that on average has a magnitude of 1/10. Those together are not going to be good for just feeding into a model and just expecting it to work. We need to deal with those differences. Too much data can actually be a problem sometimes. So if you have way too much data and it's going to take forever to run, and you have to set up like a distributed processing infrastructure, that could be a nuisance too. Too little labeled data is also obviously a problem, right? Right now, most of deep learning relies on the fact that the data sets are large and the models are large. And then another one is correlated data features. And so if you have maybe, say, I guess if you have a model that inputs height and then leg height, I guess height and leg height will roughly be correlated. Though they might be very correlated. So then having both of those features may be redundant in the end of your model, right? Because they're going to provide the same kind of a signal, right? Which is what is like the length of this person. So this is something to keep in mind. We won't deal with this today though. So it's very important to be diligent when you work with data, because if you have little bugs when you're working on the data pipeline and then you carry on with your project, little bugs can propagate into giant bugs and just completely render your model useless. So you have to be careful when you work with data. Okay, the data set we're going to use today is from this book, Machine Learning in R. I downloaded it from Kaggle. If you click on this link, it will take you right to it, but it's already in the GitHub repo, so don't worry about that. So it contains about 1,300 medical records of patient attributes and their corresponding health insurance costs. So the attributes I'm talking about are age, which is an integer, sex, which is a category, male or female, body mass index, which is a real number, children, the number of children they have, so that would be an integer, smoker, which is a category, region, another category, and charges is a real number. And then the goal is to, given all of these attributes, the goal is to predict the charges that the hospitals bill the patients. And so we're going to be utilizing heavily this library called pandas. And this is an extremely popular, extremely useful data science tool that basically allows us to store data in these thing called data frames, and then we can manipulate data very easily once we have that. So let's get started. So first thing we're going to do is we're going to read in our data from our data directory. So really simple, we'll just call the pd.readcsv file, and then we'll type df.head, and df.head just returns you the first 5 rows. And so we'll see here we have a 19-year-old female, and she's being charged, that looks like quite a hefty amount. She's a smoker. Let's see, and then the rest are males, and looks like number 3 is comparable to number 0 in charge. And so yeah, so you just want to get a good look at your data and kind of get a feel for it. Okay, data pre-processing. This is where the bulk of the work happens. I do apologize in advance. This may be kind of dull because this is not the fun part of machine learning, but it's the most important part. Okay, so let's introduce some basics of data. So the data that are input to your learning algorithm, the X's, are sometimes called covariates, predictors, or features. For this tutorial, we're going to refer to them as features. Okay. data can either be categorical or numeric, as you saw above with smoker, region, and sex. So in machine learning, categorical data needs to be converted into numerical data, right? Because how is your model that just performs a matrix multiplication, how is it going to matrix multiply a string, right? So we need to convert it somehow into numeric form. And there's many ways to do this. Two ways right off the top would be word embeddings for text or one-hot encodings. And then we're going to stick with one-hot encodings today. Now, if you're in a supervised setting, the outputs you're trying to predict are called variates or labels, and we'll stick to the word labels. So just be aware of this. Okay, so right, so I pointed out the categorical columns in our data set. It's going to be sex, smoker, and region. And then we're going to one-hot encode those. So first, I guess, topic is exploratory data analysis, or EDA. EDA is a very important step when you're tackling an unknown data set or a new data set. So basically, it's the act of like probing and analyzing your data set so you can gain a better understanding of its structures and what manipulations to apply to it, right? Because most of the time in the wild, your data set is going to contain at least one of these nuisances here. So you want to have a good understanding of how your data is structured so that you can address those nuisances if they're present. So yeah, it's very important. So first thing we're going to do is going to be called a bivariate analysis. This is basically saying, look at the correlation matrix. And why is it called bivariate analysis? Because on the correlation matrix, we're always comparing a pair of features against each other, okay? So first thing we'll do is we'll run this cell here, which is show correlation matrix. And by the way, these helper functions that are visualization functions, these are in the file visualizations.py. So if you're interested, you can look at those in your own time. So let's go ahead and visualize this correlation matrix. And so how do you compute this correlation matrix? Basically, all it is you take all the data in one column, all the data in the other column, and you compute what's called the Pearson correlation coefficient. And this you would have learned in Stat 100 or if you took AP Stats in high school, you would have learned about this constant too, or coefficient too. But yeah, that's pretty much it. And so obviously on the diagonals, it's going to be a perfect one correlation, right? Because a variable is always going to be correlated perfectly to itself. And the point of doing this analysis is to address this nuisance right here. So if we have two features that are very correlated, then we want to drop them. We want to delete them from our data set. Luckily, we don't have anything that looks like it passes over 0.8. If there was anything over 0.8, then we would have considered deleting both of those variables. Okay, so right now we're good. The bivariate analysis is done. What we're also going to do is we're going to visualize the labels that we're interested in, which is the charges, right, against all the other variables. So we're going to visualize charges against region, smoker, children, BMI, sex, age. So, but we realize that we need to treat these differently because we can't just plot along the x-axis regions and then smokers or sex, right? Because those are categorical variables. So for the categorical variables, we're going to plot box and whisker plots. And then for the continuous variables, we're going to plot scatter plots. Okay, so now we have these bivariate plots. And so as you can see on the y-axis for all of them is going to be charges. And then on the x-axis are all the features, right? So looking at sex here, we see that males get charged slightly more, right? Their third quartile is higher than the females. From this next one, we can see that smokers are significantly charged more than non-smokers. And then we see that there's really not that much significant effect with the region in your medical charge. So moving on to the bottom, we have our scatter plots. we see this weird looking pattern with age, but we do see a general linear trend. It's a very weak linear trend, but there is a linear trend there. For body mass index, there's also a very weak linear trend. You can kind of pick it out, I guess, because there's these 2-point clouds. I guess the densest part of this scatter plot is kind of flat, but we can still approximate this to have a linear sort of trend. And then for children really is sort of like a categorical variable, but since it came to us as a numerical variable, we're just going to treat it as one. And we see here there's also a very weak negative linear relationship. Okay, so from doing EDA, exploratory data analysis, we now need to go about feature selection. Feature selection is the process of selecting the data that will have the most impact in our predictive model. And by the way, I've included links to all these topics. So if you're curious about these things, you can check out these links in your own time. Right. So we want to drop columns that aren't important to us. And if we do this, then we can significantly reduce the model complexity, right? Imagine having 1 million features as input to a model versus 5 features, right? And features is interchangeable with columns here. And it also speeds up the optimization process, right? The matrices aren't as big. So yeah, so like I said, there seems to be a very significant correlation between charge and if you're a smoker or not. So we're definitely going to keep this. There seems to be good signal coming from this particular feature, smoker. From the scatter plot, since we can observe weak linear relationships on all of these, then we'll go ahead and keep all of these. And then these other two, the sex and region, we're going to go ahead and drop them. Now, feel free in your own time to add them into the model. Try adding all features into this model and see how it does. For now, we're just going to drop both region and sex because they don't seem like they have a high correlation. So let's go ahead and drop them and then visualize the new data frame. So we can see here that those columns were dropped, and now we're only working with these 4 features and this label. All right, 100 encodings. So now recall that we've dropped 2 categorical columns, but we still have smoker. So how do we convert this into a numerical form such that a matrix multiplication can handle it? So the way 100 encoding works is really simple. If you have a set of categories like dog, cat, fish, you can map it to 0, 1, 2. The ordering is absolutely arbitrary, but it's really important that you maintain that ordering and you be consistent about that ordering throughout your entire project, right? Because if the 1 and 2 get swapped at any point, then that can just screw up predictions later in the future. So if you have a discrete set of objects, pick an ordering for it and stick with it for the rest of the time. Okay. So luckily, smoker is a binary variable, so it's really easy to just map it to 0 or 1, right? And so we'll just go ahead and do that. And you can also try things like it doesn't have to be 0 or 1. It could be -1 and 1. It could be 100 minus 100, right? But the whole point is to map it into unique IDs. So let's go ahead and drop those, replace those values, and then we'll look at our new data frame. And so now you see we have our data frame where everything is numeric now, which is good. So let's proceed. Feature scaling. Okay. Feature scaling. So right here, I wrote up a little thought experiment. So imagine you have a data set that includes timer measurements from 2 different timers, measuring 2 different physical processes. So imagine that these 2 features don't have any correlation. Now, if one timer measures in nanoseconds and the other measures in seconds, and we want to feed this data into our machine learning algorithm, then the data measured in nanoseconds is going to be washed out basically by the signal from the data that measures in seconds, right? Because the nanoseconds are 10 to the 10 to the 9 times greater than all the data measured in nanoseconds. So this is a problem. I mean, you can just take this into the limit and just imagine if you had one column full of infinities and one column full of zeros, right? The column full of zeros is not going to matter at all. So we want to balance the level the playing field a little bit. And so there's many ways to do feature scaling, many ways. So I included it in this link here. But the way we're going to stick to today, and perhaps it's probably the most popular way done in practice, is called standardization. And so these are how percentiles are computed actually. So all it involves is taking each data point in each column and subtracting by the column mean and dividing by the column standard deviation. And basically this effect what this does to the data is it centers it around 0, and it makes sure that the variance is 1 around the mean of 0. Okay. So it's essentially just the centering operation and scaling, center and scale. So let's go ahead and do that. So here what we're going to do, and notice that we can only do this with our real valued data, right? So children and smoker, these are integers. And well, actually with age, we also do this with age, but age is a little bit bigger than children and smokers. So we're going to normalize age too. So we're just going to extract these columns out, find the mean for each column, find the standard deviation for each column. Then we're going to subtract the means, divide by the standard deviations, and then create our new data frame. So now we see here that all of our features are on a very level playing field, right? They're all around the same kind of magnitude. Then the charges, we don't usually touch the labels. Okay, cool. So now train test split. This is I believe this is the last part. Yeah, okay, good. We made it through. We're almost done with the data pre-processing. Train test split. This is also very important. So now that we have all of our data, you may think that we can just go ahead, pick a cool algorithm and then fit it all on our entire data. But we can't do this because we won't actually know how we're modeling the actual data distribution. Okay, if we do this, we have no guarantee that we're actually faithfully learning something about the data. So this is why we need to split our data set into one subset for training and one subset for testing. And this way we know. So basically then how it's going to work is we train on the training set and then we test on the testing set. If the error from the testing and training is relatively close, then we know that we're doing a pretty good job of generalizing, right? And so it's also common to introduce a third split called the validation set, but this is primarily to help you choose hyperparameters. And we'll see I'll introduce this concept in section 4. So yeah, don't worry about this now, but if you're interested, you can read up on something called k-fold cross-validation. So let's go ahead and just take 80% of the data as training and 20% as testing. And then we'll separate features from the labels, and then we're going to get into the good stuff, the really fun stuff. So line by line here, all this is going to do, and by the way, when you're dealing with these libraries here that have a lot of functionality, a lot of functions, and so you may not really understand this, but the documentation is your best friend, right? They understand that a lot of people use these libraries, and they try to make the documentation very readable. Okay, so the first line, what this does is it's going to shuffle everything first. Because what if we had an ordering where all the 0 children were on the top and all the 4 children and n children are at the bottom? If we just took a split at an arbitrary place, then we would be introducing a bias in our data set. We want everything shuffled around uniformly, and this is why we do the shuffling initially. Okay, so now we're going to insert this column of all ones in the very beginning, and I'll explain later why we do this, but this is also important. So I guess overlook this for now, we'll explain it later. So basically how we're going to take an 80% training split is we're just going to multiply the length of the whole data frame by 0.8, round it to an integer, and then use Python slicing, or I guess this would be pandas slicing, to make the split. So this is just saying, give me all of the rows from the beginning to the end and stop at split, whatever split is. And then this one is saying, give me everything that you didn't get from that previous line. Okay. So now we're going to separate the features and the labels. So I'm going to create this mask here. You don't have to do this. So this is just I guess this is just a more efficient way of doing things. But basically this is saying only give me the labels, right? So I only want the labels because I have a 1 in the last column. And if you recall, charges is in the last column. Okay. And so this way we're just going to be able to separate. Just imagine drawing a line between smoker and charges and then separating them into X and Y. And those are going to form our data label pairs. So let's go ahead and run this. And then let's visualize our table. So for train X, which is our training inputs, we have that auxiliary column, right, of all ones on the left, and then some subset of the data. It looks nicely shuffled. And then the corresponding charges on the right, and then same thing for this. And so last time I checked, this was about, so you can see that the training set is about 1,000 examples, and then the testing is around like 200, 280, 300 examples. Okay. So now before I move on to actual linear regression, I'll just pause here for any concerns or issues.
Yeah, for sure. So let's see if we have any. Yes, there was one question that someone asked about feature scaling. So since the two timers have no correlation, why are they compared? Data points from the seconds timer is different from the second timer.
Why
I think
are
they meant second from the first. Yeah.
Yeah, well, in this hypothetical situation, you're assuming that you're trying to model something, some physical process, but you want data from both timers. We're inherently assuming that these two timer measurements contribute to the actual label, but they themselves have no correlation. But they may both have a contribution to the what is it called? The variate or the labels, right? So that's why.
Perfect. Yep, that's about it for now.
Okay, cool. Okay, linear regression. This is where we dive into the fun stuff, the math. And so you may have heard of linear regression before, and it may sound simple, but we'll see. I'm not sure if any of you have taken 446, CS 446, then you guys should be pretty familiar with this. But I guess for a beginner, this should be a pretty good amount of stuff. So the linear model. So now we're going to take a dive into the linear model. And so it turns out that many situations and processes in the real world can be modeled with a line or a hyperplane. That would be a generalization of like a line. And after all, if you zoom in far enough on any curve, you'll see a line, right? And that's like a creed that physicists live by, right? Have you ever taken physics 211 and you are doing the harmonic oscillators, and you saw the approximation that sine x equals x for small values of x? That's like a linear approximation. So recall that this is the equation for a line in 2D. If we want to extend this to multiple dimensions, then because our data set is multiple dimensional, right? It's 4D, it has BMI, age, children, and smoker as features, then we need to utilize matrix notation effectively, right? We don't want to work in this notation. This would be a pain to write out and it would take forever. But if we encapsulate everything in matrix operations, then it's going to be much more efficient. So notice that if we have multiple features, then we need to have a slope for each of those features, right? And then notice that we can write this actually as a dot product. And a dot product is just taking two vectors and then multiplying them element-wise and then adding them together, right? The two vectors need to be of the same size. And hopefully you can see why now we added that column of ones along the left side of our data set. Because this is effectively, when we do this dot product, it effectively accounts for that bias term here. So the theta sub 0 is our bias, right? It's the intercept, the y-intercept. And so So that means that our data vector and our parameter vector, our thetas, is going to be one dimension more than what our original feature dimension was. So we have 4D right here, but now this means that we're going to have 5D data vectors and a 5D parameter vector, right? For a line, you could have equally written this as a vector MB times a vector X1, right? So this is why we added that column of ones along the left side. So right, we can just write this as a simple dot product, and then yeah, look how much cleaner that is, equation 1, than this nasty sum here. Okay, yeah. And then D is the dimensionality of the features. Notice how the X vector was augmented with a 1. Yeah, has the same effect as adding a bias when you actually take the dot product. Okay, now let's define some things. So we're going to design a matrix X, capital X, where we just take all of our augmented data vectors, that is with a 1 on the very first entry, and then we're just going to turn them into row vectors and stack them on top of each other. So this vector is going to have a shape of n by d plus 1, right? This is just saying that this is a member of the real valued matrices of this shape. That's what this fancy notation means. So this is called the design matrix. Yeah. Next, we're going to define the parameter vector, which you saw up here. And basically, this is going to entirely encode our model, right? This is all you need for linear regression. It's just a vector of d plus 1 numbers. Yeah. So as you can see, this is an element of the real d plus 1 by 1 matrices, aka vectors. And the parameter vector, kind of the same thing. This encodes, oh no, sorry, reading the wrong line. This contains the y hat, specifically contains the predictions, right? So y hat contains what your model predicts given some x and your parameters. And this is an n by 1 vector or matrix, right? This is just a column vector, 1y for every data point. And then obviously y without the hat here is going to be the label vector. Basically what we take directly from here, from the test y, train y. Okay, so now this is like one of the best tricks to debug machine learning algorithms, in my opinion, is to always just look at the matrix shapes. So we know that in the end, we want an n by 1 vector. So how are we going to do that? Well, if you recall from like matrix multiplication, you know that the dimensions that are touching each other on the inside that are the same, those dimensions collapse. So if we multiply x by theta, we're multiplying an n by d plus 1 with an d plus 1 by n matrix, right? And then so that d plus 1 is matching in the middle, those collapse, and then we end up with an n by 1 vector overall. So this is our linear model. Equation 2 is our entire model. It's just the matrix x times the parameter vector theta. Okay, so now very, very essential topic here is the loss function. So given some arbitrary parameter vector theta, we want to know how good it is, how good of a model it is, right? Because theta is our model. That encodes our entire model. So we want to give it a score using something called an objective or a loss or a cost function. We're going to go with loss function here. So a common loss function for linear regression is called the sum of squared errors loss function. And so starting from this line here, we can see that all it does is it takes the differences between each of the label and prediction pairs, and then we're going to square them and sum them up and divide by 2. We'll see why the divide by 2 is just there for mathematical convenience. But yeah, let's crunch through this math a little bit. So we know that y hat is going to be this, basically xt theta, and then you can convince yourself, if you write out the terms in the sum, if you write them out, you can convince yourself that it's actually a dot product, right? It's a dot product of y minus our predictions, right? So the vector y's minus our prediction vector, dot product, And this, furthermore, is equivalent to the squared L2 norm. And so let me just unpack this last line, equation 3, a bit. So these double bars on both sides. So right now, the quantity on the inside is a vector, right? So it's just, ignore that there's a minus sign, just treat it as a vector, because that's what it is on the inside. The double bars indicate a norm. And basically a norm is something that you define over a vector space. And in this case, the subscript 2 on this norm, the subscript, indicates that it's the L2 norm. And L2 norm is the exact same thing as the Euclidean distance, right? How do you find the diagonal of a triangle with x, y as its legs? You take square root of x squared plus y squared, right? That's just the basic Pythagorean theorem. And so this is generalizing it to higher dimensions. And plus we need to take a square on top, right? Because we don't have on this line, we don't have a square root. So really we're taking the squared L2 norm, and that's all this is. Now this may seem like a very arbitrary choice of loss function, but it's actually theoretically motivated. So there's a lot of theory actually behind linear regression, and this is not an arbitrary choice at all. If you're really interested about the theory and motivation of why we use this, then I left a link here and you can go ahead and check it out. Basically, if you approach this problem from a Bayesian perspective, a Bayesian probability perspective, then this loss function naturally appears in the math. It's quite nice to see. Okay, so the interpretation I like of the sum of squared loss is, since I'm a physics major, by the way, is placing one end of a spring at every data point and then fixing the other end on some point on the line. The point directly, I guess, if you were to draw a line through a vertical line, wherever it lands on the line. And so assuming all the springs are equal strength and the line is free to move and the data points are fixed and there's no gravity, if you started it off at a random initialization and you just let it go, then the line would kind of oscillate and then it would find its natural equilibrium. And this natural equilibrium is the best fit line. So this is kind of a visualization here. So yeah, so if you just put this line through here, you can see here that there's this roller track thing they're trying to show that shows that the line can I guess rotate. But yeah, this is the interpretation I like of the sum of squared errors loss. So let's go ahead and implement this loss function. And so we're going to use NumPy's linear algebra library. And if you just use norm without any extra input arguments, this by default gives you the L2 norm. And then, yeah, and then we want to square this, right? Because we're taking the L2 norm squared. So this is the SSE, or sum of squared errors. And then let's just take a random theta, right? And then let's just see how well it does on the test data. So I'm going to randomly initialize on this first line here. I'm going to randomly initialize a theta from the standard normal distribution, which means I'm just going to randomly generate numbers that are centered around 0 and have standard deviation of 1. So let's go ahead and see how well it does. So that's our error, pretty high, right? Very, very high error. This is the average error, by the way, where we divide by the length of the test set. Okay, so obviously we feel like we can do better than this. So let's see, how do we actually find that optimal parameter vector theta? So yeah, the remaining question is, how do we actually get this best fit line? So notice how the loss function is a measure of how good our current parameter estimate theta is given the data. Lower is better. So if we have the parameters that fit the best fit line, then the loss itself should be low. In fact, it should be at the lowest it can go, because if we look here, we see that this is actually a quadratic form. One thing that we know about quadratic forms is that there is a unique minimum, and if there's a unique minimum, that just it just follows that that unique minimum is the global minimum. That's the best possible you can do. So to find the optimal theta, we're going to use tools that we learned from calculus 1, calculus 2. And that's just you take the derivative of a function with respect to a variable, and then you set that derivative equal to 0, and that gives you the point, right, where the function is stationary at or it has 0 slope, aka a minimum or a maximum. But since we know we're working with the parabola here, we know that we're only going to have a minimum. But in practice, you should check if it's a minimum or maximum. Okay, so yeah, by doing this, we're guaranteed to find the best fit line because there's only one minimum because we're working with a parabola here, or a hyperboloid, I guess, since we're in multiple dimensions. Okay, before we dive in, we need to define some matrix derivatives. Now, I don't expect anyone to know matrix derivatives off the top of their head. I had to look these up, but these are essential for the derivation. And these are actually not that hard to convince yourself that these are true. Basically, all you do is you write out so this is a matrix vector product. All you have to do is you write out the actual sum and the matrix, like you write out the scalar variables, and then if you take the derivatives, you can see why these are true. So let's dive in. I'm going to be using this notation here. This is called nabla. This is the gradient of the loss function, but don't worry too much about that. Okay, so let's just take the derivative of theta of our loss function, okay? So first thing we're going to do is we're going to expand our loss function out. Then we're just going to do the vector version of FOIL, right? So we're going to take the first times, okay, well, I don't remember what FOIL actually means, but we're going to take this one times this one, y times this one, and then we're going to go here, multiply by this one, and here by this one. So we see here we end up with a yty, and then a minus ytx theta. Then since we have the rule that the transpose of AB, where A and B are matrices, is the transpose of AB is equal to B transpose A transpose, and this is why you see a theta t xt instead of a theta t xt instead of a xt theta t or x theta t. So yeah, so then at the end we have the theta t xt x theta. And then you'll see why that we have a 1/2 here. It's just to cancel out any 2's that appear in the derivative. So then moving from here, we're gonna employ a little trick. I claim that these two are equivalent to each other. Why are they equivalent? Because recall that let's look back at the shapes of these quantities. If we look at this product here, we recall that theta is d plus 1 by 1, so theta t is 1 by d plus 1. X is n by d plus 1, so xt is going to be d plus 1 by n, and then y is going to be n by 1, right? And so if we multiply this product out, let's look at the shapes. The inner dimensions here are the same, so they collapse into 1. These inner dimensions are the same, so they collapse. So everything is 1. So that means we have a 1 by 1 matrix. And a 1 by 1 matrix is nothing other than a scalar. And so taking the transpose of a scalar just returns the scalar back itself, right? The transpose of a scalar is essentially the identity function. So that's why, so if we notice here, this term is the transpose of this term, and that's why I can combine them in this manner, okay? And then also notice here that this first term, yty, has no dependence on theta. So when we take the derivative, this term is going to zero out, okay? So now using our matrix derivative rules, moving from this line, moving from this line to the next one, from 4th to 5th, using our matrix derivative rules, we're going to get this, and then we're going to have 2's on both. So then the 1/2 will take care of that. And then we'll have this expression for the derivative. Now, if we set this to 0, we can move one thing to one side, And then we can move this matrix, we can multiply by the inverse of this matrix to get our final expression for the optimal parameters, which is just this. Quite a clean, beautiful derivation of a very powerful model. Yeah. Okay, so this matrix here, notice how originally we were trying to solve the system of y equals x theta, right? So you might have been wondering why we couldn't just do x inverse left multiplied by x inverse on both sides. Well, that's because x is not a square matrix. You can't take an inverse of a square matrix. So it turns out that there's been some theoretical work done on this particular matrix here. This is called the Moore-Penrose pseudo-inverse matrix. And basically what this is it's a generalization of the matrix inverse, and it can be applied to rectangular matrices, which is very powerful. So this, you can see that this equation kind of takes the form of theta equals x inverse y, but it's not actually x inverse, it's x. In math, it's often written out as like x dagger, and that's the pseudo inverse. So this is nice. This is really a clean expression. So we can just utilize NumPy's at operator. If you guys have never seen NumPy's at operator, it's awesome. It's basically just a way to do matrix multiplication like you would use with the asterisk or the plus sign. And then we're also going to use the transpose attribute to get the transpose of a matrix. And then this equation here is entirely all of what we just gone through. So all that work for one line of code. So this just implements equation 4. And then we're going to just go ahead and turn this into a NumPy array. And then we're going to print the optimal parameters. And we'll see here we get something, okay, we don't really know what to think of it for now. But let's go ahead and run it. Let's predict on the test set and see what the, let's see what the sum of squared errors is on the training set and the test set. So we see that the test loss is something on the order of, what is this going to be? This is 20 million. This is 160. This is 160 million. So we can clearly see that the optimal solution is much better than the random guess solution, basically. And then if we look at the training loss, we see that it's less than the test error, which means that we may be overfitting a little bit, right? So it's not, the gap is not too far, but if the gap were to increase over time, let's say if we weren't doing this, but rather we were doing an iterative algorithm, and we saw that this gap was separating between the train and test loss, then that would be a good indication that we are overfitting. Okay. So this is great. We got a couple of numbers. We got the machine to spit out a couple of numbers, but then now what? Now we need to engage in what's called interpreting the model, right? Visualizing the results. So this is equally as important as the data pre-processing and the learning algorithm itself. In fact, there's a whole field dedicated to model interpretation. Yeah, and especially in deep learning, because deep learning models are even harder to interpret or to dissect. So I left a link here, and there's like it's just like literally a whole online textbook on model interpretation. So again, let's visualize the bivariates again. Remember, we want to drop that column of ones because it's not important to us. Okay, so these are the lines that the model has fit to our scatter plots. We can see here, we can notice across all of these that the line passes through the regions of highest density, right? This makes intuitive sense because if there's a region that's more dense, there's going to be more points there. If there's more points there, there's going to be more contribution to the actual loss, to the sum of squared errors loss, right? Since this, so for example, take a look at the charges age plot, the second one. Those kind of like diffuse clouds above this dense point cloud, those basically what the model has learned, I guess, or has optimized for, is that they have less contribution to the loss than the actual number of points in this dense point cloud here. And so we get kind of like rough approximations of rough lines of each of these scatter plots. This last one, charges and smoker, since we turned smoker into a numeric column, right? It was able to actually plot a scatter plot of this. And we can see that this does exactly what we would expect linear regression to do, which is given two lines, we would expect the lines to split the difference, right? Right in the middle of both lines. Well, not exactly right in the middle, but approximately. So yeah, the best fit lines on all of these strikes through the denser regions, and this is what we would expect. And so that's why the model is okay with not touching these more diffuse point clouds. And then also another interesting thing to notice is that this last feature is the highest. But what does this last feature correspond to? This last feature actually corresponds to the smoker column, right? And then if we go back to our bivariates beforehand, we see that there was actually a really, really strong correlation between how much you're charged based on your health insurance and whether or not you're a smoker. Okay, so intuitively, our results make sense to us. And this is literally the best it can do on this data. Okay, regularization. This is an especially important part of machine learning. There are people who dedicate their lives to studying regularization in machine learning. So basically, we want to ask the question, is this model the best model? Well, like, is our linear model the best linear model for this data? So what if those point clouds were actually corruptions, right? What if these were actually noise points from a really bad sensor or something? Or what if they were just the way the data was collected and handled, right? What if they were errors, or what if our parameter values are too high? What would a lower norm solution look like if we had all of our magnitudes in this parameter vector lower than they were, right? Essentially, our model may be overfitting. And overfitting is when the parameters are too fine-tuned to the training set and thus provides overconfident, poor predictions on the test set. So we want to regularize our model, which is basically a way of saying we want to penalize our model based on complexity. So you may ask, how do we actually measure model complexity? And there is many ways to do this, like a lot of things in machine learning. There's going to be a whole branch of literature based on this one little topic. So the way we're going to measure complexity today is with well, first of all, let me introduce the new loss function. So the way we're going to basically regularize is we're going to add this term, this R term that depends only on the parameters, modulated by a lambda. And this lambda is a constant that just adjusts the strength of how much we care about regularization. So for this tutorial, we're going to look at the squared norm of our parameters as the regularizer. Now, basically, if you think about it, if the norm of our parameters is very high, then that means the loss is going to be high. So then that means that our model is going to penalize very high norm parameter vector solutions. So basically, if it sees this large parameter value in smokers, it's not going to like that, and it's going to penalize that. Okay, so this is called L2 regularization, or if you're fancy, Tikhonov regularization. The good thing about this new loss is that it also has a global minimum. So that means that we're compelled to use the same procedure as before, right? We're going to differentiate this loss with respect to theta, set the expression equal to 0, and the solution that's going to be spit out is this. So I'm not going to do this derivation. I'll leave it as an exercise to the reader. But basically, it's the same procedure, right? You just take the derivative, you use those matrix derivative rules, and yeah, it shouldn't be too hard to get to this solution. But basically, The only thing that differs is that we now have this added term here, which essentially all this does is it adds a small number, or it adds the number lambda to every element on the diagonal of this matrix, right? If you recall from here, we have nothing inside of this parentheses, but now we have this inside of the parentheses. And that is the only difference. And so this solution is what's called ridge regression. This is a very, very popular form of regularization. And yeah, if you work in machine learning, this is something you're going to see a lot. So basically, it gets its name. The reason why it's called ridge regression is because if you look at the optimization landscape and you plot the contours of the loss function, you're essentially following like a ridge along the loss landscape of the regularization term. If that just went completely over your head, I'm sorry about that. I understand. But if you're interested in diving deeper, I did provide more resources right here in this link. And so a fun fact actually is that ridge regression came from the 70s when a bunch of computer scientists noticed that computing this matrix inverse was very problematic. So there was a lot of numerical instability associated with it, and this was because of what's called the condition number of the matrix. If you want to learn about condition numbers of matrices, I also provided a link here. So basically, the way you alleviate that numerical instability is you add a small number to each term on the diagonal. And so that's exactly what this lambda I was. But like surprisingly, this gave better statistical predictions. And then so it was pretty much discovered by accident, this whole new branch, very rich branch of theoretical machine learning that is very useful in practice. So let's go ahead and implement ridge regression. So literally I just copied and pasted this line here, put it in here, and then added the lambda times the identity right there. And that's it. And then you return the NumPy array of theta values. Okay, so now here's what we're going to do. So how do you choose the best value of lambda? So in practice, in machine learning, you're going to have a lot of different knobs to turn, right? A lot of different values to choose from. So this is actually where that cross-validation that I mentioned earlier comes into play. What we're going to do here is we're going to basically define a range that lambda can live in, and then we're going to try every single lambda in that range. So we're going to try lambda from 0 to 10, and then we want to split that into 100 equal intervals, and then just try every lambda in between that for that vector of lambdas. And this is basically cross-validation, right? Because all it is that you try a value of a hyperparameter. A hyperparameter is basically a parameter that you get to tune, you get to adjust by hand, and then you look at the loss. You jot it down, and then you try another value, look at the loss, jot it down. This is basically what we're going to do. But do note that in practice, it's not as, you can't always just do this, right? Because you may have way too many parameters to try. So basically all this does is that I get a list of lambdas that I'm interested in trying. And then for each of those lambdas, I'm going to run ridge regression and then record the best possible theta, the best possible error, and the best possible lambda value that we get. And then we're going to plot the test errors as a function of lambda. So let's go ahead and run this. Oh, don't forget to run this cell first. So it's still going. Okay. So here's our test error, here's our plot. So we see that actually if we increase lambda, then we're going to reduce our test error. This is a very good thing. So we could have even pushed this even more, right? We could have cranked lambda up to 100 and seen how well we would have done. And this is why I wanted you guys to create a copy of this notebook so that you can turn these knobs yourselves and see for yourselves. In fact, why don't we just go ahead and try the range 5 to 20. and then see, okay, so now we have a nice parabola shape, right? Past a certain point, we're not going to do any better than lambda equals 10.30, 30, 30, 30, 30, right? From there, our test error goes up. So now let's see. So yeah, so turns out the best error doesn't actually occur at lambda equals 0. So we can see that we actually benefit from regularization here. So now if we compare side to side the previous values in our parameter vector with our new parameter vector values, we see that in general, the values are smaller, give or take. So like the first entry is bigger, and then this entry 463 is bigger than 405, but then the rest of these are smaller than the other parameters. And this is what we wanted, right? We wanted to penalize very high magnitude values in the parameter vector, because this is just how we measure, this is just how we choose to measure model complexity. I would also like to note that this doesn't, you could have also chose the L1 norm here, right? You could have chosen any general norm. You could have chosen what's called the LP norm, which is basically you replace this 2 on the subscript with the P, and you vary P by integers. And so those will give you different solutions to this problem too. If you choose, instead of a 2 in the subscript, if you chose a 1, that would be called lasso regression. There's a bunch of special names for everything. Okay, let's visualize these bivariates for the best one. So not much different, right? I guess the only immediately visible difference, well, I can't see any actually. So not much different, but the loss was reduced, right? So if we compare the loss, this is 200, what is it? This is 21 million. Up here, we had 21 million, okay, 21.3 million. And then down here, we had 21.3. Oh, we also have 21.3. Let's see. 21. Okay, we're going to just have to compare number by number. 21 through 23. Oh, yeah, sorry. So this one is a 21, then a 38, and then this one is a 21, then 23. So it's visibly much lower than the previous test error. So now let's go ahead and see. Let's really go ahead and play around with lambda and visualize how these best fit lines change when we change lambda. So kind of give a spoiler here, but what if like we cranked it up what if we really cranked it up? What if we made it negative? What if we made it really small? Things like this. And so here's where you guys can really sort of play around. First thing you should check to verify yourself is if you make it really big, then we should get a flat line, right? Because we would really be penalizing any sort of big magnitudes in the parameter vector. So if lambda is really big, I should expect to see flat lines, and that's exactly what I observed. If I kind of like take it back a notch and maybe do 100, we kind of see that they're the same, but notice that in this fourth plot here, the smoker, it seems like the line tilted down a little bit. If we look up here, the line was kind of passing right through these two things and then passing through the middle of the denser region on the left line here. Now it looks like it kind of like rotated downwards, right? Because we have lambda at 100. So what if we made it negative though? What if we made lambda negative 100? So think about what this is doing. If we make lambda negative, then that means that we would be penalizing low norm solutions. So that then we would get very high norm solutions if we made lambda negative. If we get high norm solutions, then sure enough, we get some explosions. Yeah, for some reason right now, the smoker best fit line is wants to explode, but the other ones looks like the intercept value, the bias term theta sub 0 got pushed down, and I mean we can get really crazy here. And so if you get too crazy, then you just get absolute garbage solutions, right? And if you And if you make lambda really small, like 1e to the minus 6, then we see that it's pretty much no different from our normal linear regression solution, right? So this is essentially no ridge regression at all. And there's always that sweet spot, right? So our sweet spot was 10, but you can choose it to whatever you would like. And so that's pretty much it for this tutorial. I hope you guys learned something. Yeah, I hope you guys visit some of the links, because the best way to learn machine learning on your own is to dive into the information yourself and try to decode whatever you're reading for yourself. So is there any questions so far? Anything on the Slido?
So yeah, one of the questions that we actually did get was kind of along the lines of what you ended on. They were curious to know what resources you use to kind of learn all this stuff, and any practical resources you have that you could link them to kind of learn more.
Yeah, I could go through. Let me just go through them right now. So I'm still sharing my screen, so just follow along with me. I guess you can just jot down these learning resources yourself. So actually, what I started with after I graduated high school was Google's ML crash course. So I thought this was a very, very good high level. It's completely free. It's a very good high level introduction to machine learning. Back then, I only cared about neural networks, I guess. But now I'm starting to realize that you need to build a foundation from the bottom. A good way to do it is build foundation from the bottom up if you're serious about machine learning. If all you care about is applying models in your job and trying to push numbers, right? That's perfectly fine. Then you don't have to learn this way from the bottom up. You can just import scikit-learn or something, and then just do model.fit, and that's totally fine. That's justified. But if you want to learn either way, if you're serious or you want to do that, I would recommend this course. It's just enough detail. Yeah, it's just enough detail to get started. There's a lot of good content in here. Pretty much the most important concepts that you can learn at a very high level, though. Very high level. It's not very deep. But yeah, you see that there's even the ML engineering section here. So if you just care about, if you're a software engineer and you want to maybe apply machine learning to your problem, then this would be good for you. Yeah, ML systems in the real world, it's really good to know how these things get done in practice. So I would highly recommend this. It's all you type in Google is Google machine learning. What did I type in? Machine learning crash course. Yeah, Google ML crash course. Another great resource, if you're very, very serious, is Chris Bishop's pattern recognition machine learning textbook. So this used to be the gold standard textbook for many years on machine learning. But then once the revolution came along, right, when machine learning kind of blew up, Microsoft actually open sourced. So Chris Bishop is a researcher at Microsoft. Once that explosion came along, they open sourced it. So now you can get it for free online. I have a copy. Where is it? Mine's right here. And I frequently refer to this textbook when I'm unsure of something. Yeah, I think this is a really good textbook to go through. It can be very heavy in some chapters, but it's probably the most thorough coverage of machine learning that I've seen, next to Kevin Murphy's probabilistic. Yeah. So definitely these two books basically have the most in-depth coverage of like everything in machine learning that I've seen. But another way to, like, the best way to learn is to just get your hands dirty yourself, pick a data set, pick a problem, and just dive right into it. Implement a neural network from scratch. This is what I did. That's what I did in high school when I was starting to really get into it. Yeah. So additionally, another good learning resource is going to SIG AI meetings. Like, don't mean to plug my organization here, but we try to do a good job of teaching both from a theoretical aspect and from a hands-on coding aspect. So yeah. Are there any more Slido questions?
I think that's about it for now. Jeffrey,
Okay.
do you have anything else to add?
Yeah, so come next semester, we'll be doing our SIG AI meetings online, most likely through Zoom. But yeah, I guess I don't know where to post, where I could like post information about this, but if you're interested in learning more, I would recommend going to our meetings. We host two types of meetings. We host a theory driven meeting where we basically go over like research papers. This is for the more like seasoned practitioners. And then we have a sort of like a coding meeting, which is for all levels, where we basically just code things up like this. But this is probably more in depth than we would go in our coding meetings. This is very this is a huge deep dive here. But yeah, that's pretty much it.
Yeah, and as far as you were saying, Jeffrey, about resources, you can actually just send them over to me, I guess through Zoom chat if that works. And then
Cool.
we can actually put them in a Discord post that we have after all of our workshops and events where we kind of summarize what happened. And we can link those for our attendees in the Discord so they have access to them also.
Yeah, cool.
So yeah,
I'll send those over to you after this then.
yeah, sounds good. But yeah, on that note, thank you everybody for attending. We hope you kind of learned a lot from this deep dive, as Jeffrey mentioned, and that you can find some use out of it, not only for, obviously like learning for the sake of expanding how much you know about ML and CS in general, but also for your projects that you're working on at HackThis. We hope it'll be helpful for that. On that note, we'd like to say that David Hardy is speaking actually in less than 30 minutes now. So we do encourage you to come out to his talk. He'll be talking a lot about, the inequity that education kind of poses and ways to overcome that, especially when we talk about remote learning. Definitely something worth checking out as far as ideation goes for this event. I know a lot of people are still in that phase. So if you're all thinking about the actual problem that you'd like to tackle when it comes to the project that you're making at HackThis, please come out to that talk. We'd really appreciate it there. Yeah, with that being said, thanks everybody once again for tuning in and have a great rest of your Sunday. Cheers.
All right, thanks guys. See ya.